In the dynamic landscape of Web3, tokens are evolving far beyond simple digital assets. They're the lifeblood of decentralized economies, enabling new forms of governance, finance, and social and environmental impact. But to truly harness their transformative potential, we need to understand the underlying mechanisms that drive their optimal use and shape the communities they serve. In this tutorial, we'll explore how game theory helps us analyze expected behavior and design aligned incentives. We'll uncover how cyber-physical systems and control theory can be applied to token-based systems, illuminating how they adapt and self-regulate to ensure stability and longevity. And finally, we'll examine how mechanism design can help craft rules and incentives that encourage truthfulness, fairness, and overall system efficiency. Through real-world examples like bonding curves, prediction markets, and conviction voting, we'll showcase how these powerful tools coordinate social behavior and drive positive outcomes. In our previous tutorial, we discussed that markets aren't just a place to buy and sell stuff. They're intricate systems of rules that shape our collective well-being. We explored how markets can strategically be designed to incentivize participation, aggregate preferences, and foster effective decentralized decision-making. As Friedrich Hayek eloquently put it, markets act as a marvel of information processing, utilizing price signals to efficiently allocate resources across a vast network of participants. Trust and well-designed rules are paramount in this process. They reduce transaction costs and create a level playing field. For markets to function effectively, these rules must align individual incentives with collective goals, encouraging actions that benefit the entire system. However, markets are not without their challenges. Incomplete contracts create principal-agent issues that lead to inefficient outcomes. Fortunately, innovative market design informed by game theory and other analysis techniques can help us reduce their effect by designing incentive-compatible systems. Adam Smith's vision of a free market, unburdened by rent seekers who extract value without contributing to it, remains an aspiration. But as Eric Beinhocker reminds us in The Origin of Wealth, economics often operates in theory, detached from real-world complexities. This disconnect can have painful consequences. As Mike Tyson famously said, everyone has a plan until they get punched in the face. Without grounding our economic systems in empirical data, we're vulnerable to unforeseen shocks and suboptimal outcomes. Game theory is a powerful framework for understanding strategic decision-making. It helps us analyze situations where many people interact, each pursuing their own goals while also considering the actions of others. In any game, some people may choose to cooperate or compete, while others may just seek to benefit without contributing. At its core, game theory assumes that individuals are strategic actors making rational choices to maximize their own selfishness. Although behavioral economics shows that this isn't always true, this concept allows us to model and predict behaviors in complex systems with many interacting players. Consider a blockchain network. Validators, users, and developers all have different goals, yet their actions collectively shape the system's performance and security. When designing crypto-economic systems, game theory becomes an invaluable tool. It helps us anticipate how participants might behave under different incentive structures and mitigate potential vulnerabilities like collusion or market manipulation. By modeling various scenarios, we can create robust token economies that remain stable and beneficial even when participants act in their own self-interest. Auction design is a prime example of game theory in action. In first price auctions, like an art sale, bidders should strategically underbid their true value to maximize their potential gain. By how much depends on what they think others are bidding. In contrast, second price victory auctions incentivize bidding your true value, regardless of other players' strategies, since it's mathematically guaranteed to be optimal. However, victory auctions are vulnerable to collusion, and typically regulations aim to disincentivize it. By applying game theoretic principles, we can create robust, self-sustaining systems that encourage desired behaviors while discouraging harmful ones without relying on centralized control. This approach is essential in crypto economics, where traditional governance mechanisms often don't apply. Game theory encompasses various game types, each with mathematical insight into their optimal strategies. Knowing which strategy to use for analysis in which game is critical for designing effective mechanisms in complex systems. Simultaneous games involve players acting concurrently without the knowledge of each other's choices. A classic example is rock, paper, scissors. Finding the Nash equilibrium, that is, where no player benefits by changing their approach, is the key strategy in this game type. In automated market makers, this could mean finding the optimal balance of liquidity required to maximize rewards while minimizing risks. Sequential games see players taking turns, with later actions influenced by earlier choices. For example, chess or negotiating a deal. Crowdfunding and peer-to-peer equity platforms exemplify this, where investors assess project proposals and then decide whether to contribute, influenced by the actions of prior investors. Cooperative games, like team sports, are where players collaborate to achieve mutually beneficial outcomes. In decentralized autonomous organizations, cooperative game theory is crucial for designing governance mechanisms that encourage collective decision-making and resource allocation. Non-cooperative games assume players act independently, prioritizing their own gains. For example, a stake pool operator competing for delegation to maximize their rewards. Finding a dominant strategy or Nash equilibrium is the key for this game. For example, EcoPool's verifiable 33% monthly donation towards environmental charities is a likable incentive for delegators with a sustainable worldview, since the pool operator bears the expense. Repeated games are particularly relevant to token economies. Robert Axelrod's Evolution of Cooperation highlights how repeated interactions can foster trust and collaboration even among selfish actors. This is analogous to a perpetual motion machine, where the incentive to maintain a positive reputation for future economic interactions fuels ongoing cooperation. Leader-follower games, also known as Stackelberg competition, offers insights into scenarios where one player acts first, influencing the subsequent actions of others. This dynamic is evident in bonding curves, where the curve creator sets the parameters and traders react accordingly. Sigmoid curves, for example, incentivize early adoption while deterring speculative behavior, contributing to a more stable and predictable system. By using these game types to help us analyze situations, we can tailor mechanisms to produce positive sum interactions where one person's gain is also the other person's gain. I highly recommend you play Nicky Case's 30-minute game, The Evolution of Trust, linked below, to understand these concepts further. Cyber-physical systems offer a powerful lens to understand how programmable digital token flows interact with the real world. Advancements in technology enable digital systems to not only affect but record the real world, effectively bridging digital, human, and physical realms. In Cardano's extended UTXO model, programmable token flows record individual decisions. When designed well, transaction outputs seamlessly become inputs in a continuous flow, allowing the system to self-regulate. References to data packets, along with their measurement and verification, each potentially recording real-world actions, can be anchored to these transactions. This wealth of verifiable data becomes invaluable for understanding and improving complex system designs. Analyzing the recorded interactions between digital tokens and real-world actions provides insights into cyber-physical systems' effectiveness and identifies areas for optimization. This data-driven approach allows for the continuous refinement and adaptation of cyber-physical systems, ensuring they evolve to meet the changing needs of our interconnected world. Control theory, the field of study within cyber-physical systems, focuses on how systems respond to feedback. In token economies, this translates to designing mechanisms that adapt to market fluctuations, user behavior, and external events, ensuring the system remains stable and achieves its intended goals. This dynamic interplay between control theory, token economics, and real-world data is at the heart of effective cyber-physical system design. The cybernetic model depicted here illustrates how system-level behavior emerges from agent-level responses to rules and incentives. This feedback loop allows for decentralized autonomy. By creating and refining rules and mechanisms, we can steer the system towards desired outcomes without controlling the often uncontrollable individual actions. Furthermore, having near real-time tamper-proof data accessible on a shared UTXO ledger allows for near real-time steering of our digital economies, giving ourselves the best chance to make informed decisions by putting humans first and letting machines handle the cognitive load. Stafford Beer once said, "The purpose of a system is what it does. meaning a system doesn't do what it claims to do or what it promises to do, but by what it actually does. Tools like CAD/CAD and real-world verifiable data empower token engineers to verify and optimize their token designs through modeling and simulation so that the system does what it actually promises. CAD/CAD helps us make informed, rigorously tested decisions on how best to modify or interact with the system in order to achieve its goals. Monte Carlo simulations test for randomness and variability, accounting for uncertainty and identifying potential pitfalls. Parameter sweeps help identify the optimal combination of inputs for desired outputs, while A/B testing compares different models to determine the most effective design. CAD/CAD can also be easily integrated with common data science workflows to assist with computer-aided governance. By embracing these principles, token engineers can create responsive, resilient, and autonomous systems that thrive in the complex interplay between the physical and digital realms, unlocking the full potential of tokens for social and economic impact. Financial systems are an integral part of economic systems, and with all capital flows the potential for manipulation and exploitation. Designing secure and reliable financial cryptographic systems is a complex challenge, requiring expertise across diverse and often contrasting disciplines. Ian Grigg's Financial Cryptography in 7 Layers is a valuable model that helps conceptualize the field of token systems. By examining each layer and its interactions during system design, we can identify and address potential vulnerabilities and ensure a robust and secure foundation. For example, another construct by Grigg that spans layers 3 to 6 is the Ricardian contract. With incomplete contracts and technical implementations, there will always be misunderstanding or manipulation, which means any token system must define what the token system does at a human scale and have provisions for dispute handling. A Ricardian contract bridges legal and technical systems, creating a human and machine-readable agreement. By incorporating legally binding terms directly into smart contracts, we can interface with legal systems, streamline transactions, reduce the cost of dispute resolution, and enhance overall transparency and trust. Cryptography and good software engineering are paramount for decentralized financial applications. Cardano's native asset support, a fundamental feature of the platform, allows for the creation and management of custom tokens directly on-chain, leveraging the network's proven decentralized consensus mechanism. This eliminates the need for simple smart contracts for tokens like the ERC20 or token bundles like the ERC1155, reducing costs and vulnerabilities while ensuring a more scalable and secure system. Owning capital is essentially the power to design, organize, and transform the economic resources of a social system. Owning tangible resources like shares or utility tokens, whose financial value may increase over time, clearly provides benefit. However, intangible resources like social status or governance tokens can also provide benefit, since whoever has the governance authority over a pool of important resources also has the potential to direct some of those resources back to their own benefit. This concept of governance as capital highlights the importance of designing fair and transparent governance mechanisms that distribute power equitably and ensure the long-term health and sustainability of the system. Mechanism design is the art and science of crafting rules that align individual incentives with collective goals, making it the cornerstone of token engineering. It's about identifying desired outcomes, whether economic, social, or environmental, and designing systems that naturally guide participants towards them, while discouraging harmful behaviors. It draws inspiration from 3 key areas. Contract theory explores how agreements between parties can be structured to achieve optimal outcomes, even in the face of uncertainty and asymmetric information. Auction theory looks at how people strategically behave in auctions and the design of auction rules to achieve specific outcomes like maximizing revenue or efficiency. Matching theory provides insights into how individuals or resources can be paired in a way that is both stable, for example, no one wants to switch partners, and optimal, that might mean maximizing overall welfare. The work of Nobel laureate Eric Maskin highlights 3 essential properties of well-designed mechanisms: truthfulness, individual rationality, and efficiency. That is, participants are incentivized to report private information truthfully, they are better off participating than not, and the mechanism achieves a desirable outcome for the system, such as maximizing total welfare or minimizing costs. In decentralized systems, these principles are critical for sustainability. Let's consider a few examples of powerful mechanisms in action. Bonding curves create dynamic incentives for buying and selling tokens. The leader strategically sets curve parameters to maximize their objective, whether it's bootstrapping liquidity, stabilizing price, or achieving a specific fundraising target. Followers, or traders, can then calculate the exact price impact of their actions based on the curve's equation, leading to more rational decision making. Conviction voting allocates resources based on the continuously expressed preferences of participants over time. The longer a choice is held, the more weight it carries. This mitigates the drawbacks of plutocracy, Sybil attacks, and last-minute vote swings. Prediction markets allow participants to bet on outcomes such as project success or failure using, you guessed it, tokens. And because there is skin in the game, these markets tap into collective wisdom and incentivize honest information sharing. These mechanisms and many others can be employed to solve specific challenges, like attracting early adopters to new platforms without penalizing latecomers. More importantly, well-designed mechanisms are essential for creating token ecosystems that not only function effectively, but also reward positive social outcomes. They are the tools we use to transform potential conflicts into powerful collaborations, harnessing self-interest for the collective good. Our exploration of game theory, control theory, and mechanism design has revealed powerful tools for shaping token economies. These concepts allow us to create ecosystems that align individual motivations with collective goals, adapting to change while driving social and economic impact. From predicting behavior with game theory to autonomously steering systems with control theory and crafting incentives through mechanism design, we've seen how these principles can address challenges in decentralized systems. Examples like bonding curves, conviction voting, and prediction markets demonstrate their practical applications. As blockchain technology evolves, even more sophisticated applications will emerge, revolutionizing economics, governance, and global interactions. In our next tutorial, we'll delve into the practical aspects of designing and managing token economies, exploring governance, network effects, legal considerations, and techno-ethics. The journey of token engineering is just beginning. Let's use these tools wisely to shape a more cooperative, sustainable, and equitable future.